Good morning, everyone. Let's start a new day from this workshop. And it's my great pleasure to introduce the next plenary speaker, Professor Vesna Zupanovic from Croatia. She will talk about oscillatory integrals and the fractal dimension. And please join me to welcome Professor Vesna.
Thank you so much for inviting me here for this nice workshop. It is my first time in Brazil, so I'm happy to be here. Thank you for giving me opportunity to give a talk here. Thank you. Okay, I will talk about oscillatory integrals and fractal dimension. Oscillatory integrals are basically objects which are related to singularity theory, since asymptotic expansion of the integral is related to toric resolution of singularities of phase function. And from another side, fractal dimension. Fractal dimension could help to explain fractals. But some objects could be regarded as fractals, even if they are not usual fractals. Here we will not have usual fractals, but we will obtain some additional information about these objects by fractal dimension. These objects will be curves defined using oscillatory integrals. Basically, in my talk, I will show results obtained at our paper, joint paper, with colleague Jean-Philippe Roland from Dijon, France, and Domagoj Vlah from University of Zagreb. Something is with sound, but okay. I think it will be okay. Motivation. Our motivation basically comes from dynamical systems. Our first object, which we regarded in our articles, were coming from dynamical systems. Also, I would say the motivation from fractal geometry comes from a very nice, beautiful book from French mathematician Claude Tricot, Curves and Fractal Dimensions. So Claude Tricot regarded smooth curves as fractal objects. I will say, of course, more in my talk. Then basic definition says fractal dimension, but which one? There are a lot of fractal dimension. Which one will be useful for us? Now you can see that, that it is a box dimension, but there are also a lot of names for this box dimension. Box counting dimension, Minkowski dimension, limit capacity, so on. Then I will show first result of the group. It is result obtained with colleague Darko Žubrnić from Zagreb, related to a spiral weak focus, defined by very simple dynamical system and related to Hopf bifurcation. Then I will show our joint results about singularities of, okay. I already said that motivation comes from dynamical systems and from book of Claude Tricot. He says that curves are also smooth curves are also fractal objects. If you have, for example, spiral with infinite length accumulating at one point, by integral you will obtain that length is infinite. But if you plot this object, this curve, spiral, by some software, by some tools, you will see that you can change parameters and you will see that your infinite length could be bigger or smaller. You will see accumulation near the origin. If this curve accumulates to one point, you will see that there are black circle which is bigger or smaller. So fractal dimension can say more about this, but which one? I would say that the most popular fractal dimension is still Hausdorff dimension. But Hausdorff dimension doesn't see what we would like to see. This is accumulation at one point. Hausdorff dimension is not useful for such curves because of countable stability. If you cut a curve at countable many curves which are rectifiable with finite length, you will obtain the dimension is the maximum. It's just one, and you don't see anything. But with box dimension, you can see the difference regarding the names. It is, I would say, maybe the most popular name is box counting dimension, because a very popular definition of that box dimension is by counting boxes, but it is very useful for numeric. We don't use this definition. There are a lot of equivalent definition. Our source of knowledge from fractal geometry is basically from books of Scottish mathematician Kenneth Faulkner. There are two very nice books, and you can obtain equivalent definitions for box or box counting dimension. At our first article, we were using box dimension, but now I think that maybe Minkowski dimension is the most suitable name. You will see later why I think so. Limit capacity is also quite a popular name from 90s. A group from IMPA, they were using this name limit capacity in order to obtain some more information, and so they had a lot of results about homoclinic bifurcations related to fractal dimension. But this is box Hausdorff and also a box dimension called limit capacity. Hausdorff dimension coincide with box dimension if you have classical fractals accumulating at a lot of points, like Koch snowflake or Sierpinski carpet or Sierpinski triangle. It is the same Cantor set. But for these objects which are accumulated to one point, this is different. So also, to regard dynamical systems and fractal geometry all together, this idea is not completely new. In 70s and 80s, there were a lot of results obtained by mathematicians and also physicists. They were trying to explain complexity of strange attractors using this fractal dimension, different fractal dimensions. But our point of view, research group in Zagreb and our collaborators is a little bit different. We compute box dimension of an orbit of dynamical system. Motivated by Claude Tricot, we started with curves, with spiral curves. They appear in dynamical systems related to oscillation in phase plane. You have spiral, you have focus. This is very interesting. And also discrete dynamical systems are very interesting objects for fractal geometry. Basically, bigger dimension, box dimension, is related to very slow convergence. Slower convergence means bigger dimension. Poincaré map is Poincaré first return map. It is a standard tool which connects continuous and discrete dynamical system and unit time map and so on. So we had a lot of things to study in discrete and continuous dynamical systems. Even that spirals, which I mentioned, that spiral could go to point. Of course, that spiral can be accumulated to a limit cycle, closed, isolated closed curve, and also spirals could be accumulated at polycycle there. So there are a lot of things to do. But what about what about singularities of maps? We noticed that by oscillatory integral, a curve could be produced. Something like this. I will show on another slide. But here, this is weak focus, which we will study as a very simple result to show the idea. We call it weak focus if eigenvalues of Jacobian are pure imaginary. This is called weak focus. Weak focus is simple because after blowing up resolution of singularities, in weak focus, there are no other singularities. So when we regard Poincaré map, for example, in any direction, the asymptotic is the same. But there are also in our research, we had also different type of focus, nilpotent focus with nilpotent Jacobian, and also degenerate, which means no linear part, but they are different and there are still open problems there. Chirps. From Tricot book, we obtained these two formulas for box dimension, which will be defined soon, for these two objects. Chirps are related to oscillatory going to the origin. For example, it is very nice to measure oscillatory in infinity, switching infinity to zero. Colleague Domagoj had his thesis was regarded to Bessel function and oscillatory and fractal properties of Bessel function, well-known Bessel function, and sequence. On the line, it is very simple to see and to compute box dimension of the sequence. It is immediately seen multiplicity of the function which generates the sequence. So if you know box dimension of this sequence accumulating here, you will know immediately the multiplicity of function generating this sequence. And oscillatory integrals. Here is example in R. This is maybe I would say the well-known example. Clotoid or Euler spiral or Cornu spiral. There are several names. It is spiral defined by Fresnel integral. Fresnel integral is also the oscillatory integral. Some years ago, we started to study clotoid. I was at some conference and we just had our first result about weak focus. I met their Bulgarian and French mathematician, Vladimir Kostov. Vladimir Kostov told me, have you ever heard about clotoid? I said, in fact, no. He was using clotoid in some optimal control things. So I paid attention to clotoid, and then we obtained some results, fractal results about clotoid, and later on we realized that there are much more interesting things related to these oscillatory integrals. For example, this phase function, if you have something like this, and C is not zero, and you have this continuous, we call it amplitude, that this call it phase, F is phase, V is amplitude. You can obtain something like this and something like this with C equal to 0. But okay, we have some results, but still not for such objects. Okay, what is box or box counting or Minkowski dimension? We are using this definition related to Minkowski content. So that's the reason why now I think that Minkowski dimension is the best name. We take a bounded set and then epsilon neighborhood. A epsilon of A, it is epsilon neighborhood of the set. And then we take Lebesgue measure of that epsilon neighborhood of the set, which means if you are on the line, this is length, epsilon length of epsilon neighborhood, or in dimension 2, this is area, and dimension 3, and so on. And then we divide with this, and we obtain something called upper, as dimensional upper Minkowski content. For now, we can take just a limit to explain a little bit better. Okay, here you have S and you have Minkowski content. If you divide with small s, this is infinite. Your content is infinite, and then it drops down to 0. And you could, or not necessarily, you could obtain here this point. We say that moment is not moment, but parameter of dropping is called box dimension, upper, analogously lower. In fact, what does it mean? You compute area or length of epsilon neighborhood of set, usually orbit, and you can see the leading term and coefficient in front of the leading term. It is Minkowski content, and dimension could be read from exponent. So if you have first this leading term, exponent, from exponent you see dimension, and from coefficient you can see the Minkowski content. But of course, that this definition is suitable for powers. You can see here just powers. It is possible that you have this area or length, that leading term is logarithmic. So in that case, it drops from infinity to 0. And there are more definitions which are generalized definitions with some kind of gauge functions. Here there is a group of fractal geometry doing a lot of such things. Group is in California, University of Riverside. Leader of the group is Michel Lapidus. And so they are using also gauge functions suitable for other types of epsilon neighborhood. So, okay, if limit superior, limit inferior are the same, then you have upper and lower box dimension, and I'll call it a box dimension. Okay, we need this just to say that functions are comparable near, for example, 0, if this quotient is between two constants. It's the technical thing that we really needed. And also, if the Minkowski content is not 0 or not infinity, we say that some object set is Minkowski non-degenerate. If there is some that coefficient in front of the first term, then it's Minkowski non-degenerate. Okay. Okay, formulas, Claude Tricot formulas. Spiral in polar coordinates. This spiral, we are interested in accumulation near 0, near origin. So for this alpha, spiral is non-rectifiable, I mean with infinite length. This is box dimension for this type of spiral. So here you can see this type. Maybe to say that for alpha equal 1, you have dimension 1. It's dimension 1, but this curve is still with infinite length. So in such cases, it is some kind of boundary cases, then Minkowski content is infinite. It means it's Minkowski degenerate and Minkowski content is infinite. So if your box dimension is non-trivial, it means if your curve is bigger than 1, then you obtain information directly from box dimension. But if your box dimension is 1 and still is infinite length, then Minkowski contents say that you are in fact fractal object. Chirps are also, it's the same thing for alpha equal to beta. So this is chirp. And this for sequence, it's in fact, it's not from the book, it's well known. It's for high school students. You can try it. A equal to 1, 2, 3. High school student could obtain this formula. So it is quite obvious that if A is bigger, then it goes to 1. Of course, here it goes to 2. So this is related directly to multiplicity. I said multiplicity of the function generating the dynamical system, one-dimensional. Okay, this is our first result about weak focus. This is standard normal form from old Taken's article. For L equal to 1, you have something like this. Then you can see this system here, that for A0 bigger than 1, it's strong focus, it's hyperbolic. It's in fact exponential spiral. R is equal to E2 minus something or plus something, it depends. Okay, this is strong focus, but this is rectifiable curve. If you compute length of this, you will obtain some number. Okay, this is hyperbolic, we are here. We start from here, from right to left. And then real part of the eigenvalue of Jacobian disappears, and we have weak focus. Weak focus, it is infinite length of the curve from the point of view of curve. This is something like this. It is possible to apply, very simple, to apply Tricot formula, and then we obtain 4/3 for this curve. And then when we go there, A0 is smaller than 0. Again, we have strong hyperbolic focus, but limit cycle is born. Here you can see that here limit cycle is born. So it was some kind of motivation that by a box dimension, we can estimate quantity and quality of objects which could be produced by perturbation of the system. This is here, if you find somewhere, and you know that it's weak focus, with dimension 4/3, then you know that after perturbation, just one limit cycle could be born. For L is equal to 2, it is well known that 2 limit cycles could be produced. Theorem says this, that, okay, if you have hyperbolicity means to be exponential. Yeah. No. Exponential, and then dimension is 1, it's trivial. And then you are looking for the first k, for non-zero k, and you obtain this dimension. It means, okay, k equal to 1 for this, for third, and if we have k2, it is, here is 8, then it is 5. This spiral, 8/5, by perturbation could produce 2 limit cycles. 2 limit cycles could be produced by perturbation. So bigger box dimension means bigger potential that this object produce more objects in bifurcation. This is Hopf bifurcation. This is called Hopf bifurcation, but this is called also degenerate or generalized Hopf and Hopf-Takens bifurcation. Okay, so what about singularities of maps and this fractal point of view, something like clotoid, but more complicated. So this is oscillatory integral. You can see that parameter tau is here. This function is called phase function. This is called amplitude function. So here is Rn, from the first example was just R, okay? And then we can define a curve by this parametric equation. This is a real part of the integral, and this is imaginary part of the integral. So by this, we defined the curve. And we noticed that this curve has bigger box dimension if singularities of the phase function are more complicated. Basically, more complicated. Okay, so this is our case. So we have very nice amplitude, and we avoid this type of spirals with 2 frequencies, something with spring, so on. We have just these cases, which are some kind of direct generalization of the clotoid case. Phase first amplitude function, class C infinity, non-negative function with compact support. Point 0 is inside the compact support of the function. And this phase function is analytic, and 0 is critical point or singularity of the phase function. It's the only critical point inside the compact support. So here we define our curves. We define curves. Okay, we already had this. Oscillatory, we define oscillatory and curve dimension. Oscillatory dimension dimension will be dimension of chirp. Basically, if you study just one component, you will have something like chirp. You already had this. So we put infinity to 0 in order to measure oscillatority. Okay. Then this, okay. And oscillatory dimension are defined as box dimension of graphs of this function. So we'll have two oscillatory dimensions for each curve. And this is curve dimension is, we take dimension of the curve defined by parametrization of x tau and y tau. Okay, first, our first result. Our results are organized as for dimension 1, n equal to 1, n equal to 2, and bigger than 2, basically by the dimension of a space of integral Rn. Its integral is over Rn. Okay, here we have phase function and amplitude function. Say that 0 of phase function does not coincide with singularity or critical point y. Of course, that we really relied on classical Varchenko results. We used the classical Arnold Varchenko book, and here in that book you can obtain this formula. Another slide, it will be in with more details, that you obtain this. So if f of 0 is 0, you don't see oscillatority. You just don't see because you have no sine and cosine near this term. So we needed this condition. And then it is okay, it is in fact standard multiplicity. And then you can see that with bigger multiplicity, oscillatory and curve dimension are bigger. Oscillatory dimension, it is in fact a chirp. You can remember that chirp had alpha and beta parameters. It is chirp with alpha 1 over p and beta equal to 1. Since we fix beta equal to 1, with oscillatory dimension, we cannot reach 2. So, because we fixed beta, but alpha can vary. So, with very big p, it goes to 3 half. And with curve dimension, you can see that limit is 2. You have, if you have much more complicated singularity with big p, this is bigger. So here is dimension is going to 2. It explains more complicated singularity. So, and here is Minkowski content. Minkowski content here, this C1, it is related to amplitude function. It is related amplitude function. It is known basically that for this oscillatory integrals, coefficients are related to amplitude and exponents are related to phase function. So this is our Minkowski content, which will be, I would say, more interesting in higher dimensional cases, because then we have these things that dimension is trivial, but Minkowski content goes to infinity to show you that you have no just rectifiable curve, that you have something much more complicated. So that's the theorem which we use from the book. It is very standard theorem, but maybe to show you something which will be interesting in n equal n2, dimension n2 and higher dimensions. You can see here that there are logarithmic terms. But if n is equal to 1, you have no logarithmic terms. So is n equal to 1, obtain just powers. So in our cases, we have just non-Minkowski, non-degenerate cases, just powers. Okay, Newton diagram. We had Newton diagram here in several talks and then posters. Also in my thesis, I was using Newton diagram, but in some other kind of things for vector fields, because topological equivalent between vector fields could be considered via Newton diagram, principal parts, so on. And in fact, these things for maps are the first result, and then it was developed for vector fields and systems. Okay, here we have a power series with real coefficients. We have monomials. I put here with bigger dimension. And I think you are familiar with this. And Newton polyhedron is the convex hull of the union of all translated positive orthants. I will show you an example. And Newton diagram is the union of compact faces of the Newton polyhedra, just compact cases, compact faces or sides. Okay. And what is also important here, important is that there is a principal part of the map, and there is a non-degeneracy by respect of Newton diagram. What does it mean? Okay, you put your exponent. You want here, okay, maybe, not much, okay, maybe this, and then I will come back. You have some map, you obtain here 3, 2, here is 0, 0, 0, 5, here is 5, 5, and you take something like this here, something like this here, and then convex hull. And this is all of this. It is Newton polygon for two-dimensional polygon, generally it's polyhedra. And then there is just one compact side. There is just one compact side, and here there are two non-compact sides or faces. So Newton diagram, it consists of this point and this point. It is called principal part. It is called principal part. And coming back, what does it mean, non-degeneracy? Non-degeneracy means that you take you take monomials of each side. In my example, we had just one compact side, but it could be more compact sides. You take one compact side and you see if there are, for derivatives, this is one side, and you make derivation with all variables, and you can see, is there any common zeros, I would say, outside of x's, if you are in R2. You make derivation, and you can see, is there any common zeros outside of the x's? If not, it is Newton non-degenerate. It is important in toric resolution because of monomialization that you have no other curves. Okay, and for oscillatory integrals, there is something which is very important. In my thesis, I was doing with principal part. I defined generalized principal part for vector fields, but at that time I didn't know that this remoteness of Newton diagram is directly related to oscillatory integrals. What is remoteness? Here, okay, this is by y is equal to x. Here it's intersection, and then you have, it's called CC point, and remoteness of the diagram is -1 over C. It is written here. Remoteness is -1 over C. And of course, that Newton diagram is changed by change of coordinates. So remoteness of the critical point is upper bound of the remoteness of the Newton polyhedra of this, your map or Taylor expansion, or so on. So it is remoteness. Here is, this is remoteness for this. This is exactly what Weizsäcker says, that this is exponent of the leading term in oscillatory integral. Directly you can read it. Okay, so we used that for n equal to 2. What is new in this dimension 2 by respect to dimension 1? It is possible to have logarithmic terms. So you saw from some slides, then there is possible to have logarithmic terms, and this beta is remoteness of the critical point. If it's here is 0 and no logarithmic terms, these are our values: oscillatory dimension and curve dimension. So this is without logarithmic term, but there is a if beta is equal to -1, if beta equal to -1, you can see that all dimensions are 1, but that Minkowski content goes to infinity because curves are non-rectifiable. But if you take a look at dimension, you think that maybe it is rectifiable, but it's not. It's some kind of two scales if dimension doesn't say what you need. And then Minkowski content says, it's infinite. And for logarithmic term, we say it's Minkowski degenerate. But of course, that the results could be improved in style of Michel Lapidus, involving some gauge functions, that by new definition, generalized definition, we can also see these coefficients and generalized Minkowski contents, and we can distinguish cases with logarithmic terms. Here, if you have logarithmic term, that's it. It's Minkowski degenerate, and we stop here. Okay, for n bigger than 2, greater than 2, we have two theorems. One for non-degenerate, I mean Hessian non-degenerate. There are a lot of non-degenerate, Minkowski, Hessian, Newton, it's Hessian non-degenerate. Then dimension is 1. Because asymptotic expansion of the non-degenerate critical points is something like this. Here, there is something which I don't understand. Usually, the dimension, smaller dimensions, things in more smaller dimensions are easier and simpler. But here, if dimension is 1, we obtain a non-rectifiable spiral. It's non-rectifiable with a fractal dimension, box dimension 4/3. For dimension 1 is 4/3. And then for dimension 2 is 1, but with Minkowski content infinite. But if dimension is bigger than 2, it's rectifiable. Why it is less complicated in bigger dimension, I don't know. Okay, degenerate critical point for a dimension bigger than 2. So it is asymptotic expansion of the integral, and here we need Newton degeneracy. It is written R because Newton degeneracy and non-degeneracy with respect of Newton diagram, it is related to coefficients of the map. And remote, it means non-degenerate, it means degenerate, and remoteness beta. We have the same same conclusion as in previous theorem, and you can see that you have complicated with bigger beta means bigger dimension. And when you plot your curve, you will see if you find somewhere curve obtained like this and you have big accumulation, you can see, oh, it is obtained by some degenerate singularity. And then, okay, this is case, there is a case for with logarithmic and without logarithmic. Without logarithmic term is Minkowski non-degenerate. With logarithmic term, it is Minkowski degenerate. And some examples. How to, usually it is interesting how to connect these new results with some known facts, bifurcations, so on. In dynamical systems, you already said that we have connection between cyclicity, number of limit cycles, which could be produced from the system. But here, maybe we should know much more about singularity theory to continue with these topics. But here, if we have homogeneous polynomial with degree n, this is by from Newton diagram and from our theorems, it is possible to see this. With big N, it goes to 2. And also there is a relation between multiplicity of that maps. It is, okay, if multiplicity is finite. If multiplicity is finite, that's it. And bigger multiplicity produces bigger box dimension. So more complicated means more accumulation at our curve, bigger, and also another example. But here there are two parameters, of course, that we cannot directly connect multiplicity and curve dimension and oscillatory dimension, because there are two parameters here. There are two parameters, but it is obvious that bigger P and Q, they gives us more accumulation. It goes to 3.5, and here it goes to 2. The oscillatory, it is chirp, and this is spiral. It's based on a lot of generalization of Claude Tricot formula. And also, we are basically from dynamical systems, and we would like to relay these results with bifurcations and so on, but didn't do it up to now. And also interesting cases are something like this, which I mentioned in the beginning. If amplitude function is different, for different amplitude function, we can obtain this. But is it also when you compute something, is it just for computing, or you can relate to something? Yeah. We have related a lot of things with multiplicity limit cycles, but here I believe that it could be also done something similar, I'm not sure. And also non-analytic phase function. We have some numerical experiments with this type of functions if these exponents are not integers, if they are positive real numbers. And we had some experiments which said that the same results valid for curve dimension. And it is possible also, if we have these spirals, it is possible to compute via Poincaré map. But with this oscillatory integral, you have spiral. If you have spiral, you can define Poincaré first return map, and then you connect. Then it is easier to compute box dimension of the sequence. And then the sequence you connect to curve if you know that your spiral have the same asymptotic of the Poincaré map in all directions, but you can see blow up. So okay, so this is our article, which I basically talked about, and we are using also this Greenblatt article a lot because for some our cases it wasn't available from classical literature, these coefficients in front of the leading term. So we are computing some using Greenblatt, and some of them we were computing by ourselves. So, but for net-degenerate case, we had this classical things. So thank you so much. Yeah, sure.
Thank you for so good talk. Questions, comments now? Yeah.
Thank you for the talk. I have a question. Have you started considering cases where the phase function is analytic, but the critical points are complex?
No, but this also its direction. Yeah, okay. No, we didn't.
Right, thank you.
In fact, we stopped with this. You see, it's 2021. Then we stop with these topics. But after this conference, I think I will continue. I'm motivated. It's so. This singularity theory is so beautiful, in fact.
Thank you.
There are questions, comments? Okay. Vesna, I remember that, sorry, maybe not a good question, could be a stupid question, but there is a way to evaluate the cyclicity using this. Mm-hmm. And I could not understand exactly how you mentioned here I have two limit cycles. Mm-hmm. How I could see this maybe using Newton diagrams.
Okay. Maybe just it is easier with one limit cycle. So if we have A0 is equal to 0, it is weak focus. This is we know that this is a box dimension, but for example, say if you find somewhere this focus, and you can compute you can compute box dimension of the sequence. Here will be third. Then you know that you are in this case, which means this case, and then you can obtain by perturbation one limit cycle. So that's the question. But you need to know that you have weak focus, that you have some other object. So you find weak focus. You say, okay, I will take a look, make some analysis, and you take this transversal. You compute this. It is not complicated. You say, okay, I'm in this case. So since we know that we have weak focus, we are here, and then by perturbation, because we can obtain one limit cycle. So we are doing numerics. We are not very good in numerics, but now we have some results.
Thank you so much. So let's thank the speaker again. Paulinho, podemos começar? So, the next speaker is Alexandre Rodrigues from Portugal, and he will speak about, let me see if I could say, the Bock and Simon conjecture and the Cherenkov-Hopf bifurcation. So, let's welcome Alexandre.
Okay, so thank you. Thank you. So good morning. It's a great pleasure to be here. I would like to thank the scientific committee to invite me to be here. So I'm really happy. So I'm also really happy to share my recent research about the Simon and the Bock and Simon conjecture about the Hopf-Cherenkov bifurcation. During my talk, I'm going to define precisely the conjecture and what is the Cherenkov-Hopf bifurcation, okay? So, I'm from Porto, now I'm in Lisbon, and during this talk, I will not speak about singularities because I don't do singularities. However, my work is related with singularities, as we'll see, okay? During this talk, I'm going to define chaos and strange attractors. So this is the topic to which I'm more familiar. I'm going to motivate my work. In the part 3, I'm going to define the conjecture and the Cherenkov bifurcation, okay? The part 4 is a little bit technical, is about the proof, but it's just the idea, and the part 5 is about further directions. During this talk, I'm going to avoid technical details, so all details have been omitted, okay? And these parts, they are more or less independent. So if you get lost in part 1, you could come back and to the part 2 and so on, okay? So I'm going to define chaos and strange attractors, some definitions, examples, and difficulties. So, ingredients. Which are the ingredients that I'm going to consider? X is a metric space, F is a map, not necessarily invertible, and pair of F is the notation for the periodic points of the map F. Is okay? So, what is a chaotic map? There are several definitions of chaos. I'm going to use the definition of Devaney, Robert Devaney. I'm saying that a map is chaotic if, first of all, the topological closure of the periodic points is X, right? The second condition is that F has sensitive dependence on initial conditions. Alex, what is the meaning of this? It means that if you start with two conditions, X and Y, very close, okay? If you wait, so if you compute the orbit of X and the orbit of Y, so at some point, the distance is greater than a given number, okay? So this is the meaning of sensitive dependence on initial conditions. And F as a dense orbit. It means that there exists an orbit that visits all possible regions, all possible open sets. It's okay for definition of chaos. So we have definitions. Let's go to examples. Okay, what is the first example that we can teach in the course of dynamical systems? Is the quadratic family. So the quadratic family basically is a polynomial of degree 2. Okay, I'm going to assume that mu is 5. Okay, mu is greater than 4 in fact. Okay, and consider the set of points in such a way that the orbits of all points in 0, 1 fall into 0, 1. Alex, I don't understand this definition. So, for example, in the first iteration, what is the part of the interval 0, 1 that falls in the interval 0, 1? It's just I1 and I2. If you iterate again, what is the set? So I'm going to remove the middle part, okay? In the second iteration, what is the part of E1 and E2 that fall into the interval after 2 iterations? So I have 4 closed intervals, and so on. after I have 8 subintervals, and so on, and so on, and so on. And at the end, I have a dust, like a dust. This dust is called a counter set. It's not important, but it's called a counter set. And the map F restricted to lambda is chaotic, okay? There is a proof, but I'm going to omit the proof. It's chaotic, trust me, okay? This is the first example that you have in the course of dynamical system about chaos. Second example, let's complicate, is the so-called Smale horseshoe, okay? So suppose that I have a square of size 1, a square, and in the vertical direction, I'm going to expand by 3. And in the horizontal direction, I'm going to expand by 3. And in vertical direction, I'm going to contract by 3, so multiply by 1/3, okay? So then I'm going to fold and put in this form here. This is why I call the Smale horseshoe, okay? The shape is the horseshoe, okay? So I'm going to put this into the original square, and I can have the inverse of this map. So the inverse, what is the inverse? Is to contract in the horizontal direction and expand in the vertical direction. So it's possible to define F and F minus the inverse, okay? I'm going to iterate this several times, so infinitely many times, and I'm going to consider the set of points that fall into the square for all n, okay? So instead of a dust in the one segment, I have the product of counter sets. At the end, I have a counter set, okay? And I have this result. F restricted to lambda is chaotic, okay? In the language of dynamical system, we say that dynamics of F restricted to lambda is topological conjugate to a Bernoulli shift of 2 symbols, right? So it's chaotic. So we have 2 examples of chaos. What is the problem? Is that almost all points in terms of Lebesgue measure, they go away, okay? So I have chaos, however, the set of points that realize chaos, they have 0 Lebesgue measure. It's okay? So let's improve definition. And I'm going to use definition of strange attractor. Basically, I'm going to use definition of Ruel and Takens, the Ruel and Takens, and the definition is the following. Suppose that I have a diffeomorphism. What is a strange attractor? Basically, is an invariant set in such a way that there exists a dense orbit, is more or less the same definition as Devaney, with positively Lyapunov exponent. Positively Lyapunov exponent, for those that are not familiar, it means that the derivative is expanding. In average, the derivative is expanding. So points are expanding, are diverging, okay? Is more or less the same as the sensitive dependence of initial conditions. But I have here the third property is the most important. The third property is that the basin of attraction, okay, contains a set of positive Lebesgue measure. What is the meaning of this? Is that numerically I can see chaos, okay? So numerically I can see the basin of attraction. It's the set of points that are attracted to the set, okay? But this is for diffeomorphism. For vector fields is the usual definition. I say that a vector field possesses a strange attractor if the first return map to a cross section as a strange attractor. The Poincare first return map as a strange attractor is okay. Examples of strange attractor. What is the most paradigmatic examples of strange attractor? One is the Lorentz map is a strange attractor for vector fields, for vector fields. And for maps, we have the Anon map, okay? Or the proof to prove that is a strange attractor is related with a one-dimensional map. However, to prove analytically that I have a strange attractor is very difficult. For example, this Lorentz flow has been discovered in the 60s, but the final proof that is a strange attractor has been proved in the 90s by Tucker, okay? For example, the Anon map, the the discovery of the NN map started in the 70s, but the final proof has been done by Benedicts and Carson in the 90s and 2000. Okay, so it took a period of 30 years to prove analytically that we have a strange attractor. So it's difficult to find strange attractors. Okay, so there are now we are interested in finding mechanisms to find strange attractors. Instead of proving strange attractors, let's prove mechanism to have strange attractor. One of the most well-known mechanisms for strange attractors is a result by Leonardo Mora and Marcelo Viana in the 93. And he's saying the following: suppose that I have a diffeomorphism, a family of diffeomorphisms, in such a way, so I have a family of diffeomorphisms in R2. And I'm going to assume that this mu belongs to a given interval and there exists a fixed point for f mu. Fixed point is a point in such a way that this holds periodic point, a fixed point. I'm going to assume that this point is hyperbolic and the derivative of the Jacobian has two eigenvalues, one with modulus greater than 1 and the other with modulus less than 1. So it's possible to locally to have this picture, right? I'm going to assume that the product, so this is lambda, this is mu. I'm going to assume that the product of the eigenvalues is less than 1. So it's important that the point P is dissipative. In addition, I'm going to assume that for mu equal to 0 in the parameter, I have a homoclinic tangency. It means that it's possible to define here the unstable manifold. Are you familiar with unstable manifold? Okay. Let's define the stable manifold. The stable manifold of P is the set of points that are attracted to P in positive time. Okay? So I can define all these points, the stable manifold, when n tends to plus infinity, the points will tend to P. The unstable manifold is the same when I reverse the time, okay? So I'm going to assume that I have a tangency for a given parameter. Mora and Viana, they proved the following. They proved that there exists a set with positive Lebesgue measure in the parameter space, a set of positive Lebesgue measure in the parameter space, for which the corresponding map exhibit a strange attractor. So they exhibit here a strange attractor when I unfold the tangency. I have a tangency. If I move slightly the parameter, the tangency unfolds either on this way or in this way. Okay? So the result says that there exists strange attractor under these conditions. So this is a mechanism. So the problem is that I can have strange attractor, is okay. However, the basin of attraction of this strange attractor is like a pipe, is a very small pipe. The basin of attraction in general is very small. So what is the goal of my research at the moment? I would like to find systematic way to obtain strange attractors. And this is my connection with the singularities, because there is a team in Spain, in Oviedo and Barcelona, that are unfolding some singularities. So they have a singularity of a vector field, they unfold, and for some unfoldings, they find some heteroclinic bifurcations. Okay? Heteroclinic bifurcation means that I have invariant sets that are connected by trajectories. They have some heteroclinic bifurcation. In my research, my starting point are the heteroclinic bifurcations. So they have the people in Oviedo and Barcelona, they have a singularity, for example, nilpotent singularity, op, zero, hop, okay? They get, when they study the unfoldings, they have some heteroclinic configurations and they prove the existence of strange attractors. My starting point is this one, but is motivated by works in singularities, okay? And the second point is that I'm interested in mechanisms to obtain large strange attractor. But Alex, what is a large strange attractor? Large strange attractor is a strange attractor that is not confined to a small portion of phase space. Okay, it's not a pipe. Okay, it's not confined to a small portion. And there exists a precise definition of large strange attractor by Brouwer, Carl-Simon, and Thatcher. Okay, and finally is a technical result under which conditions the dynamics could be reduced to a one-dimensional map. So I have a vector field. Okay, I compute the first return map, and I have in which condition I could just study one-dimensional map to recover the dynamics of the initial vector field. Okay, so I'm finishing the first part of my talk. So please take this information. What is the main information of this? Is definition of strange attractor, okay, and the starting point is heteroclinic bifurcation. I would like to have a mechanism to have strange attractors. Take this and put in one pocket. Let's go to the second point. The second point is the motivation of my recent work, okay? The motivation. And the motivation is the Belousov-Zhabotinsky equation. This equation has been studied in the 20th century, and basically is based on a chemical reaction in which usually when I have a chemical reaction, I have two reactants that give rise to a product of two other products, okay? This reaction is a reaction in such a way that these products react between themselves and they give rise to the initial reactants. So I don't evolve to an equilibrium. I'm going to have a mixing between reactants and products, okay? I have here a movie. Podes me ajudar, por favor? Eu não sei se há pouco nós já testamos. Queria copiar esta ligação. Há pouco eu testei e pôr num browser. É que não está a dar, não dá para. Ok. E agora vai aí browser e põe.
Okay, and Kai, can you pour your solution in? So here we are. The Science Club is investigating oscillating chemical reactions. This is a modification of the Belousov-Zhabotinsky reaction. You can see that it turned dark blue when the concentration of triiodide increased sufficient to change the indicator color. And now you can watch the concentrations oscillate back and forth. Rather than reaching equilibrium in a linear fashion, the concentrations of reactants and products increase and decrease in an oscillating fashion on the way to achieving equilibrium. What do you think, guys? What's your reaction?
Really cool.
Wow.
That's better. It's a little bit fluid. And next club period, we're gonna try it.
Yeah. Nice. Okay, and Kai, can you pour your solution in?
So this is the Belousov-Zhabotinsky reaction. So the period of time in which I have one color and the other, they evolve chaotically. Okay, so the reactions are for an equilibrium. So I don't get an equilibrium. The final result is not an equilibrium, but is a mix of colors. So is chaos. And during the 80s and the 90s, there were several papers relating the two things: the Belousov-Zhabotinsky reaction with something. Let's see the abstract. The abstract says that it's possible to define a continuous flow reactor, reveal a sparring strange attractor which arises from the interaction of a local subcritical Hopf bifurcation with a global homoclinic bifurcation. There are several papers relating the Belousov-Zhabotinsky reaction with the a bifurcation that I'm going to call a Shilnikov-Opf. And from now on, I'm going to be a little bit more rigorous, okay? So this is the goal of my work, is the characterization of the Shilnikov-Opf bifurcation motivated by the Belousov-Zhabotinsky reaction, right? So let's go to the second part, okay? The third part. The second part is just a motivation. Is okay? By now, it's okay? It's not very heavy, I guess, okay? So let's define the Shilnikov-Opf bifurcation. I'm going to define a C3 vector field, okay, in R3. And this C3 vector field is 2 parameters, depends on 2 parameters, epsilon and B, okay, right? And I'm going to assume that the parameters are independent, and they are very close to 0, but they are independent. And I'm going to assume one hypothesis. Let's come back to differential equations, okay? I'm going to assume that I have an equilibrium. The equilibrium is O. Okay, I have an equilibrium, and the linearization as eigenvalues, lambda, one that is positive, okay? Let's go to the second part of the sentence. I have one positive eigenvalues, and I have a pair of complex non-real eigenvalues. Pay attention, this is for epsilon real, less than 0. So the real part of this complex eigenvalue is negative. So I have this. It's okay. It's just a picture. Okay? And now let's analyze the first part of the property. There exists a double homoclinic connection. This is a term in dynamical systems, but is basically to say that I'm going to assume that I have a situation like this. This is a double homoclinic connection. Homoclinic connection is an orbit that goes to O in positive and negative time. This is homoclinic connection, okay? This is a homoclinic connection because when time goes to plus infinity, I'm going to approach O, and when time goes to minus infinity, I'm going to approach O as well. Is okay? So this is the first hypothesis. Okay, and Alex, why do you call Shilnikov here? Because Shilnikov was a Russian mathematician that in the 60s, he studied this kind of heteroclinic cycle and homoclinic cycle. Okay, this is why I call this a Shilnikov. The word Shilnikov is explained. Let's go to the second hypothesis. Second hypothesis. I have 2 parameters. Okay, for epsilon equal to 0, I'm going to assume that I have a supercritical Opf bifurcation. Alex, what is the meaning of a supercritical Opf bifurcation? It means that this O undergoes a supercritical Opf bifurcation. So I have this situation. So O becomes unstable and a periodic solution that is stable. Periodic solution appears here. Is a supercritical Opf bifurcation. Don't forget that I'm not touching the other direction. So in particular, here, in this direction, I have expansion, right? So this is the goal of the second hypothesis, the explanation of the second hypothesis. In particular, in this case, I can define the unstable and stable manifold, and in this case, I can define the stable and unstable manifold. And how? So this is the unstable manifold of C epsilon. I'm going to assume that C epsilon is this periodic solution. And this plane is the stable manifold of C epsilon. Okay? The third hypothesis is the following. I'm going to assume that this unstable manifold will come back to C epsilon, to the neighborhood of C epsilon. It come back, okay? So I'm going to call these bifurcations dynamics associated to this configuration Shilnikov-Opf, Shilnikov because of this, Opf because O is undergoing an Opf bifurcation, okay? Alex, could you give me a picture? This is the picture that you should have in mind. Okay, so basically, the red lines can't touch because if it is unstable manifold, they can't touch once again. So they are very close, but they can't touch. So this is the idea of my heteroclinic configuration, right? This is the Shilnikov bifurcation. And Alex, you said that the parameter, the vector field is 2 parameters. So I used the parameter epsilon and the parameter b. Wait a moment, okay? So it's not, is in my mind, the parameter b. So how do I analyze this kind of configuration? How do I analyze this kind of configuration? In general, if I have heteroclinic configuration like this, I study the first return map to a cross section. So I'm going to define a cross section and define a first return map. To analyze the first return map, in general, in dynamical system and heteroclinic bifurcations, I analyze dynamics near the invariant sets and far from the invariant sets. So I'm going to define the local map near C epsilon, near the periodic solution, and the dynamics from here to here. And near the periodic solution, this is just 1 minute. It's technical, but it's just 1 minute. Near the periodic solution, I'm going to define cylindrical coordinates, and in these cylindrical coordinates, I can define a normal form. So it means that it's possible to know exactly the dynamics near, sorry, I have this normal form. It's possible to define, to know the dynamics near this periodic solution, okay? So in particular, it's possible to define some sets in which, so for example, the wall of the cylinder in which the flow goes in, okay? Because I know that the dynamics of the original flow is conjugated, is more or less the same, that the dynamics of this differential equation is more or less the same, okay? Inside the cylinder, okay? So since I know the dynamics inside the cylinder, it's possible to define that in the wall of the cylinder, the flow goes in the top and the bottom of the cylinder, the flow goes out, okay? This is basically, I know exactly the precise expression from the wall to the top and the bottom of the cylinder. So I know exactly the dynamics of the local map. Okay? R epsilon is the radius of the periodic solution, and the wall will be called the entrance section, and sigma out will be called the exit section. It's just 1 minute of technicality. I'm going to avoid these technicalities. And Alex, and about the global map. So I have an expression from the wall to the top, and from the top to the wall again. To define a first return map, I should define the composition of the maps that get the cross section. So here is where B plays a role. I'm going to assume that B is in such a way, so this is the last hypothesis, B is in such a way that the circle, the return, will not touch the green line. Is important. So this is the unstable manifold. Unstable manifold is a cylinder, and when it comes back, it will not touch the stable manifold. This is the hypothesis. So B is large enough in such a way that unstable manifold doesn't touch the stable manifold. Is important, is hypothesis. And I'm going to assume an extra hypothesis is that along the this heteroclinic connection, I'm going to have some contraction. So when I come back to the wall, I'm going to have a contraction, a very strong contraction. So composing these two maps, the global map and the previous local map, I can define a first return map, okay? First return map to the top of the cylinder, okay? This is the most complicated part, is done, okay? But Alex, we don't have novelty because this first return map is precisely the expression that Bock and Simon obtained in '93. What is the novelty of your research? Is your question, right? So, first of all, the domain of this first return map, the domain is a circloid. So it's important that the domain is a product of an interval times S1. Is very important, otherwise the results could not be valid. Okay, so let's analyze the dynamics. Let's analyze just the dynamics. In the dynamics, so suppose that here I have the wall of the cylinder, and what is this curve, red curve? This red curve is the intersection of the unstable manifold of the periodic solution with the wall of the cylinder. When I compute the local map of this, it should give rise to a to a closed curve. And if this curve is very close to the unstable manifold, it will wind around this red curve, that is unstable manifold of the periodic solution as well. So I have a contraction in one direction, and I have an expansion in the other direction, because when this curve is very close to the stable manifold, I have an expansion in the angular coordinates. So I have a contraction in the radial direction, and I have an expansion in the angular direction. So what is the object that you have here? Do you remind? An expansion in one dimension, and the other direction I have a contraction. So I have horseshoes. This is the first result. The first result is that near this bifurcation, near this configuration, I have rotational horseshoes, okay? But the main theorem is not the existence of rotational horseshoe. The main result says that for B in between an interval, within an interval, the first return map exhibits a strange attractor. Moreover, if I define this set, I have this property. The main information of this property is that the Lebesgue measure of set B in such a way RB exhibits a strange attractor is positive. So, in terms of dynamics, I have a strange attractor. It means that I can see the chaos, the Lebesgue measure is positive, is persistent because the Lebesgue measure of parameters is positive, so it's persistent, I can see in the parameter space, and is large because it's not confined to a very small portion of phase space. Okay, so this is my main result. And Alex, why do you call this the Bock and Simon conjecture? Because in 93, Michael Bock and Carl Simon, they analyzed a paper in which they related the Shirley-Cobb bifurcation with some one-dimensional map. And on the very last page, they have this conjecture. The conjecture that says that let's define this set of B such a way that some map has a strange attractor, then this quotient goes to 1. In my case, I can't prove that this goes to 1. I'm proving that it's positive. So I answered the Bock and Simon conjecture, but it's partially solved because I can't prove that goes to 1. This result just says that the Lebesgue measure is positive. And now let's go. So this is why I call the Bock and Simon conjecture, because they have this conjecture, and we try to solve this conjecture. I'm going to give just the idea of the proof. The fourth part is a little bit technical, but I'm going to avoid details. Trust me, okay? So in the proof, I'm going to use the theory of Lassa-Young and Wang. But first of all, I need to know the definition of Misurevich map. What is a Misurevich map? Suppose that I have a map with this shape, a map from an interval, compact interval to a compact interval with this shape, okay? And I'm going to assume that I have two critical points, at least two critical points, okay? So C is the critical set, is the union of critical points, and for delta greater than 0, I can define a very small neighborhood of the critical points, is the danger zone or critical zone, okay? So what is a Misurevich map? A Misurevich map is a map that satisfies these properties. The critical points when I do the orbits, when I compute the orbits, stay at a distance away from the critical set. So I have a Mizurevich map. So I have a map with 2 critical points, like this. This is C0, this is C1. So I can define neighborhoods of the critical of the critical points. And if I compute the orbit of C0, the orbit will not fall into the critical region for all n. Okay? The second part is that the phase space can be divided into regions. The region, the dangerous region, okay, is C delta, and the region outside the dangerous region. Suppose that an orbit stays outside the dangerous region for all time. If a point stays outside the dangerous region for all time, it means that I have uniformly expanding. So I have expansion all the time, because if it stays outside the critical region for all time, I have expansion. So in particular, the Lyapunov exponent is positive. And there are points in such a way that I can fall into the dangerous zone. Yes, it's possible to fall into the dangerous zone, but I'm going to fall in the dangerous zone after being in the good region time enough, so I can fall into the dangerous zone, but the orbit does not return to the dangerous zone until its derivative has regained an infinite amount of growth. It means that what is the meaning of this? Is that Mizurevich maps allow an orbit to have positive Lyapunov exponent. So the consequence of a Mizurevich map is that the critical points, they have positive Lyapunov exponent, and the orbit will travel around S1, around I, if I is S1. In this case, I is S1. Okay? Do you understand the meaning? So I have an orbit. That for a Mizurevich map, I have an orbit in such a way that the Lyapunov exponent is positive. It's okay to have chaos. It's okay. And moreover, the orbit will visit all interval, okay, after some time. This means that I'm going to shadow all the interval. So this is a Mizurevich map, and the proof, my proof, so I have the first return map, my proof uses a theory, the theory of Lassa-Young, that says that I have a strong attraction in the radial component, so strong contraction in the radial component, okay? So take this picture. I have the return map as 2 components, G, the radial, and the angular. Don't forget, the domain is an interval, an interval times S1, okay? So here I have a strong attraction, okay? Since I have a strong attraction, I can check the hypothesis of the invariant graph. So I can have the attracting graph properties satisfied. And moreover, in this graph, this second component, the angular component, is a Mizurevich map. So what is the idea that you have? Here, I have, in the radial, I have a strong contraction in something, in the radial component. I have a strong contraction. But along this curve, I have a Mizurevich map. So I have a very chaotic thing. Okay? Non-invertible. It's not necessary to be invertible. Okay? I have a very chaotic thing. I'm going to avoid more hypotheses. The theory says that it's possible to find a set of parameters in B in such a way that the first return map possesses a large strange attractor. Strange attractor comes from being Mizurevich, comes from hypothesis C3, and to be large comes from the equidistribution of elements in the S1. It means that an orbit an orbit here shadow this. Since the orbit shadow this, when I lift the strange attractor, I cover more than one small pipe. Okay? Okay, this is, I'm going to skip this. The second result is about, so here, the first result says that for B inside an interval, for B inside an interval, so B belongs to this interval, I have here a set of positive Lebesgue measure in such a way that I have strange attractor. It's not an open set, okay? Moreover, pay attention when this term goes to 0, if I plot the graph of the angular component, if this goes to 0, since this is very controlled, the graph, the graph of the graph here, this will wind around S1. So in the very fast velocity, when it winds around S1, I have this situation. And this situation gives rise to what? Gives rise to a periodic point of period 2. Pay attention, that is a periodic orbit of period 2. But is more than this. This periodic orbit of period 2 is done by a critical point. The critical point, the derivative is 0. Since this derivative is 0, I have this result. There exists a set, there exists a sequence of parameters in such a way that the first return map possesses a super stable periodic orbit. Super stable, why? Because I have the periodic orbit of period 2 is performed using a critical point in which the derivative is 0. It's just a chain rule, application of the chain rule, okay? So horseshoes and periodic sinks, they may coexist. And this is the hard part of my work, is the proof, but I omitted almost all details. So in terms of concluding remarks, what is the goals of my talk? Basically, the motivation was the Belousov-Zhabotinsky reaction that give rise to a Shilnikov-Opt scenario, okay? In my research, my starting point was the Shilnikov-Opt scenario that give rise to horseshoe and strange attractor, and basically this provides another mechanism to obtain strange attractor. So in some papers, if you have a Hopf-Shilnikov bifurcation, for sure, under some hypotheses, for sure, I have a strange attractor, a large strange attractor. Open problems. What is the open problem? What happens when this cylinder intersects here? Instead of having this picture, so it's a circle that doesn't touch the stable manifold, and if the circle touches the stable manifold. So it's an open problem. I guess that the result is the same, but the proof can't be done using the same techniques. Okay, so the proof, my guess is that the proof should be done using this result, because here I have a logarithm singularity. The first return map as a 0. When the first return map as a 0, you should be careful. Okay, and is that okay? Thank you.
Thank you for so nice talk. Questions, comments?
Agora acho que sim. My question is about the parameters. So you're trying to search for large strange attractors.
Yes.
And I was a bit, I don't know about epsilon and beta. So is this actually a 2-parameter bifurcation problem?
Yes.
Okay, because
yes.
you
One controls a global bifurcation, and the other controls a local bifurcation. One controls this epsilon bifurcation, and the other controls the height, the height to which the connection arrives. okay, is this height. So is basically, all right. Wait, is in P4. Is this B appears here. So B is the height to which the homoclinic connection arrives to the top, sorry, to the wall of the cylinder, and epsilon controls this opacification. Okay, it's precisely the description of Carle-Simon, precise description with more details, because they did this in 3 pages, and I did this in 10. Okay.
Right. Yeah. Okay, I see. But basically, when you state the conjecture, do you have easily
The
your
conjecture? Conjecture. Okay. Is
I was.
wait. Is,
That's
yeah.
why I asked.
Mhm.
Yeah, when you say lambda, there you have the beta B,
Mhm.
and what would be lambda?
Is lambda is
Is-
the expanding eigenvalue. I have the same. Is the
Lambda
expanding
is the
eigenvalue.
eigenvalue. Okay.
It's the same.
Right.
Wait. Is the expanding eigenvalue is the same.
Right.
Okay, exactly
Okay.
the same.
So Belousovsky-Zhabotinsky is actually a two-parameter.
There are several models that explains the Belousov-Zhabotinsky. For example, there exists an example with PDEs. Okay, there are several models to explain the Belousov-Zhabotinsky, but in the 90s and 90s, there appeared several papers relating the Belousov-Zhabotinsky with the Shilnikov bifurcation. Okay, and I took this paper. I don't do chemistry, but there are several papers relating the experiments with this bifurcation.
So in your context, we should find the two parameters in that model of Belousov-Zhabotinsky
Yes.
too. So,
Yes.
Okay.
My starting point in the paper, so since I do mathematics and not chemistry, my starting point is the model. And I said that one motivation is the Belousov-Zhabotinsky, okay? Because if you go to internet, there exists a lot of papers relating the Belousov with homoclinic chaos on homoclinic bifurcations.
Thank you.
Yeah, well, first a comment that I would bet that the same result holds when there's an
Yes.
intersection.
Yes, I'm sure that yes. But the proof should be different because, sorry,
Not much, but anyway.
because Lassagne theorem, Lassagne results, they ask that. Sorry. Let's go to the.
That the two curves are disjoint, right?
Yes, and they ask that. Sorry. They ask that these we can't have zeros, and if these intersect, I have singularities. I have zeros. So.
Yeah, but one thing I cannot understand is your main point is that you have a closed curve that returns, right?
Yes.
And then it gets wrapped around the cylinder. Why can't you have that in a saddle node hop bifurcation? So instead of bifurcating a circle, you're bifurcating two equilibria, but you still have the same sort of cylindrical box
Yes.
that returns, and you could have an invariant curve returning.
Yes, I guess that we have more or less the same result under some changes. But my main goal is to solve the
So okay, you're
yes,
after
but
this conjecture.
the conjecture by Simon.
Okay, now
but,
you have the Laborio conjecture.
Okay. Okay.
More questions, comments? No? So let's thank the speaker again.
Okay, thank you. Obrigado. Sim, obrigado.
Miriam, I think just a moment, please, Miriam.